Okay, so this video I'm going to be showing you how to calculate this rather complicated looking integral, which is the integral from minus infinity to infinity of 3x squared all over x to the 4 plus 5x squared plus 4 dx. And well, how do we calculate this integral? Can we use substitution? Well, no. The problem with substitution is that in the numerator we have a second degree polynomial, and that should very well be the derivative of the denominator in some way if we are to use substitution. But obviously the derivative of the denominator is a third degree polynomial, so we can't use substitution right away, at least. Maybe we can use partial integration first and then do some substitution. But no matter how we're choosing our u's and v's in the partial differentiation, we're also just going to end up in an endless loop where you still cannot do substitution on the unknown integral. So partial integration is also out of the question. But what do we do then? Well, it turns out that complex analysis can actually help us here. So one of the main theorems in complex analysis is going to be Cauchy's residue theorem. And it states that if we have a complex differentiable function, so all polynomials are complex differentiable, and also quotients of complex differentiable functions are again complex differentiable. So our function up here is complex differentiable. Okay. And we have a closed path gamma, and a closed path is going to be a continuous differentiable curve. And what makes it closed is that it has the same starting and end point. Okay. So then the contour integral of f over gamma is given by this expression 2 pi I times the sum of the residues of f in the AJs, and the AJs from A1 up to AN are going to be the points where f is undefined, and well aware that it is the points inside the region enclosed by gamma. So in this case, it will be the roots of this fourth degree polynomial where our function is not defined. And we can also calculate this residue. It's the limit as z goes to aj of z minus aj times f of z. So this is only in the case where the aj is a so-called simple pole. But what it really means is that if we have a polynomial expression here, like up here, then the aj is only a root with multiplicity 1 in the polynomial in the denominator. Okay, but how can this at all help us? Well, let's define some stuff, and then we'll slowly begin to see how. So we're going to define this gamma curve is going to be a closed path. So it's going to be the union of two paths, gamma 1 and gamma 2, and gamma 1 of t I'll define to be t, where t runs from minus r to r. And then I'll choose r as some real number bigger than 2. We'll see later why that will be important. And also we'll define gamma 2 as being, well, the traversing in a half circle with radius r. So t is going to run from 0 to pi, and gamma 2 of t is given by r times e to the ti. So this is going to give us a half circle, and we can draw gamma here. So let me see. Gamma 1 is going to be just traveling along the real axis, so from minus r to r. So this is gamma 1. And then gamma 2 is given by the half circle here. Alright, and it is important that we travel the right direction around the curve. So we're going to travel in the counterclockwise direction, or the positive direction. And this means that, well, we can see that that makes sense because gamma 1 goes from minus r over to r, and gamma 2 goes from t equals 0, which means it starts at r, and then it traverses along the half circle over to minus r. Okay, so that makes sense. So now we have a path where we can use Cauchy's residue theorem, which means that the integral of f of z dz along gamma is going to be 2 pi I times the sum of the residues. So from j equals 1 to n of the residue of f in aj. Okay. So far so good. So now let's define our f as well. We'll just write it just like we have inside the integral over here. So it's going to be 3z squared over, and then we'll notice that this denominator factors pretty nicely into z squared plus 4 times z squared plus 1. Okay, good. So now I've defined these gamma 1 and gamma 2, and let's get a feel for how the integrals look. So by definition of the contour integrals, we have that f of gamma, that's just f of gamma union gamma 2, the integral over gamma 1 union gamma 2, and then this union splits up in a sum. So we get that this is the integral over gamma 1 of f of z dz plus the integral over gamma 2 of z dz. So now let's calculate these individually, again using the definitions of the contour integrals. So the integral over gamma 1 of f of z dz is going to be equal to, well, we insert the limits. So it's going to be from the integral from minus r to r, and then we insert gamma 1 into z's place, and then we also multiply by the derivative. But notice the derivative is just going to be 1. So we just insert, well, the variable t, which we'll just call x now. So notice that this actually tends to our desired integral when r goes to infinity. So that is really nice. That is what we want. And now let's do some work on the integral of f over gamma 2. So I'll just get rid of this so we have some space. So, alright, so this is going to be a little more challenging to work with. I'm actually going to start by putting absolute value around it all, because we're going to show that it tends to 0 when r goes to infinity. So that it's easier to show that the absolute value goes to 0, then it means that the integral also goes to 0. Okay, good. So let's write out what f is. We'll just write it in terms of the original, not with the factors here. So we're going to have 3, and then we're going to insert gamma 2 of t on z's place. So we're going to have 3r squared e to the 2it all over, let's see, r to the 4th, and then e to the 4it plus 5e to the 2it plus 4 dt. Yep. Alright, so now we can, oh sorry, you have to multiply by the derivative of gamma 2. So we're going to multiply by the derivative, which is I r e to the ti. Okay, good. So we can bring those together, but let's also, while we're at it, take the I constant outside, and when we use numeric, oh sorry, we have to change this, the limits from 0 to pi as well. Okay, so it's the integral from 0 to pi, then we have taken the I out, which just becomes 1 when we use absolute value on it. Then we'll also divide by r cubed in the denominator and the numerator. So we get 3e to the 3it in the numerator, and then in the denominator we get r e to the 4it plus 5e to the 2it over r. I think I missed an r squared here, right? Yeah, definitely missed an r squared here as well. Great. Okay, r squared, sorry. Yeah, so this is over r, and then plus 4 over r cubed. Okay. But now we can use the so-called triangle inequality for integrals. It's not really the triangle inequality, but it's close enough. But while we're at it, we're also going to factor out 1 over r. So this does not have anything to do with the triangle inequality, but we'll just bring 1 over r outside the integral, and then we'll bring numeric value inside the integral. Alright, so in the numerator, this e to the 3it becomes just 1, so we'll just have 3 in the numerator. So this r we have taken out, so we have the absolute value of e to the 4it plus 5e to 2it over r squared plus 4 over r to the 4 numeric value, and okay. But now look what we have. Okay, so when we take the limit as r goes to infinity of this expression, well, these terms go to 0 when r goes to infinity. So this integrand will go towards 3 over absolute value of this, which is just 1, so it will go towards 3. But this out here will go towards 0. So actually we have that the entire integral of gamma 2 over gamma 2 of f tends to 0 as r tends to infinity. Alright, so that is actually really good, because now we can use our expression over here from Cauchy's residue theorem to calculate our desired integral, because we can just take the limit on both sides, and if we look at the definition down here, those residues do not depend on big R. Okay, so that this basically means that this expression here is actually just equal to our desired integral. So it's equal to the limit as r goes to infinity of just the integral over gamma 1, because the integral over gamma 2 disappeared. But this was what we noticed was just equal to our desired integral. So now the only thing we have remaining is to calculate these residues. Yeah, well, and also find out where they are. So let's take a look here at our function f and see where it is undefined. So we notice that 2i and minus 2i are gonna be in first, factor here are going to be roots in the first factor, and in the second factor we are going to have I and minus I. But then since our half circle is only in the upper half plane, these negative values of I do not count. But since we chose our big R to be bigger than 2, we know that both 2I and I are going to be inside the boundary of gamma. Okay, so these two are our two residues. So again, then I is equal to that. Alright, so let's just calculate it here. So our integral I is going to be equal to 2 pi I times the residue of f in I plus the residue of f in 2I. Alright, but since the polynomial in the denominator has 4 roots, we know that they all have multiplicity 1. So our root 2I and our root I both have multiplicity 1, which means that they're going to be simple poles of our function f. And that means that we can use this formula to calculate the residues. So this is going to be 2 pi I times the limit as z tends to I of z minus I f of z plus the limit as z goes to 2I of z minus 2I f of z. And yeah, f of z is obviously inside the limit. So notice in f, well, we can factor f even more. We can write it as z minus I times z plus I times z minus 2I times z plus 2I. And then we can see that these two just cancel. So we're left with 2 pi I. And then we insert I into f without this first factor. So when we insert I in the numerator, we get minus 3. And then we insert I down here, then we get 2I times negative I times 3I. Alright. And then plus, and then we do the same thing. This one cancels with this one, so we get we insert 2I, so we get minus 12 in the numerator. Then we get we get I here. Then we get 3I here, and then we get 4I at the end. Alright. So we are almost there, as you can see. So this first one, the 3's cancel, the i's become 1. So we have a minus still, so it's going to be minus 1 over 2I. But we can put the I in the numerator if we flip the sign. So this is going to be 1/2 I. And then this over here, well, the 12's cancel. And then we have I cubed in the denominator, which is going to be minus I, and yeah, and then we have the negative sign here. Oh yeah, so the negatives cancel. We get 1 over I, but that's the same thing as minus I. Okay, so that was a little quick maybe, but now we're almost there. So this is going to be 2 pi I times negative 1/2 I. Alright. So the 2's cancel. Then we're left with minus I squared I. And would you look at that? I squared is negative 1, and then we have a minus in front of it. It's equal to pi. So this very hard integral turned out to just be equal to pi. So happy Pi Day, guys. I hope you enjoyed this integral and this very cool way of solving it using a half circle, using contours and paths and complex analysis, complex numbers to solve a real integral. Yeah, great. Thanks for watching.